I'm Andrew Hastings Black, a research scientist at Leosphere, and I'm going to explain to you the principles of the new hybrid wind reconstruction. First, I'll give an overview of the hybrid method, then describe the prior art, the theoretical effects of turbulence, experimental data compared with our theory, and some conclusions. So the hybrid method is a new type of wind field reconstruction algorithm that is more accurate than existing methods. Other types of wind field reconstruction include scalar averaging and vector averaging, which are both widely used and thoroughly proven in cup anemometers and remote sensing devices. Leosphere has discovered that atmospheric turbulence exhibits two characteristic noise signatures, one that generates positive bias in scalar average lidar measurements, and one that generates a negative bias in vector average measurements when compared to cups. The hybrid method blends scalar and vector averaging together and reduces the biases caused by atmospheric turbulence by an order of magnitude, leading to more accurate lidar wind speed measurements when compared to cups. So first, let's go over the prior art, starting with scalar averaging. So here we have our lidar beam, and on the top we will have our radial wind speed measurements. So first we send our beam out in all four cardinal directions. And once we have four direction measurements, we combine them, north, south, east, and west, like this, to generate a horizontal wind speed. Scalar averaging generates a new wind speed every second using the last four measurements. So we continue taking measurements until we reach the end of the 10-minute measurement period when we have 600 measurements, 600 seconds in 10 minutes. These 1 Hertz wind speeds are averaged at the end of the 10-minute period to generate the average wind speed, scalar averaging. Now let's look at vector averaging. With the exact same data, the same measurements, we don't generate new wind speed measurements every second, like in scalar averaging. We wait until the end of the 10-minute period, and we average together the radial measurements along each cardinal direction and combine them again a little differently, north, south, west, east. In vector averaging, we generate just one wind speed for each 10-minute period using the average radial beam measurements. So we have these two types of averaging, scalar and vector. And in an ideal case with no turbulence, these equations are exactly equivalent. But there is always some turbulence in the real world, and the turbulence has different effects on the scalar and vector averages. And let's first look at the effects on scalar averaging. So here is one of the equations I showed you before. But I've replaced u and v with u plus u prime and v plus v prime. This is called Reynolds decomposition. This is a widely used technique in fluid dynamics for representing turbulent and average behavior. So our big arrows here, our east-west yellow arrow and our north-south blue arrow, these are dominant signals, the average behavior. And these little baskets of arrows represent the turbulent behavior. Now this is a very special equation with two dominant signals and Gaussian distributed noise. When you have an equation like this with a dominant signal and Gaussian noise summed together in quadrature, the values follow a particular distribution, the Rice distribution. Now Rice distributions are found in a variety of applications, including radio wave propagation, where it has a special name, Ricean fading, and in synthetic aperture radar imaging. Now the important thing here is that Rice distributed noise does not cancel out. It causes a positive bias that depends on the turbulence. Next, let's look at vector averaging. So here, again, we have one of the equations from vector averaging with our Reynolds decomposition. But note here that the turbulence is inside the summation, which means that we don't have a Rice distribution. Some of this noise cancels out, but we're not out of the woods. Summing vectors together includes both the wind speed and the wind direction. And if the direction of the wind is fluctuating, a key aspect of turbulence, the summation is affected by the turbulence, like this. As the turbulence grows, the vector average gets shorter, black to red to green to blue. Vector averaging creates a negative bias dependent on the turbulence. So we have our two new forms of our equations, and they each have theoretical biases that are shown here. For scalar averaging, we have this 1/4 sigma squared, sigma representing the turbulence, and for vector averaging, we have this -1/2 sigma squared. Now let's see how these compare to data from the real world. On the bottom graphs, the x-axis and the y-axis are the same as above. The standard deviation of wind direction on the x-axis and the bias comparing the lidar to the cup on the y-axis. The color of each pixel represents the density of points at that xy coordinate. And the black curves and error bars show the direction turbulence bin averages of the bias. They agree with the theory. Now, this is only one site. We've validated this behavior with 38 WindCubes at 8 sites, and our theory falls within the error bars of the ensemble average behavior. In the WindCube v2.1, we combine the two methods and reduce the sensitivity to turbulence by an order of magnitude. With a 2/3, 1/3 weighting, the direction turbulence sensitivity drops out, and the WindCube hybrid wind speeds agree much more closely with the mass data. And we can see this in the final IEC classification class at 120 meters. This is the example I'm showing here. For scalar averaging, the uncertainty is 4.4%. For vector averaging, 2.1%. And for hybrid averaging, 1.1%. So in summary, Leosphere has invented a new wind field reconstruction method derived from first principles that greatly reduces the WindCube's sensitivity to turbulence. The theory behind the hybrid method has been validated in field campaigns using high-quality net masts, and the hybrid method is now standard on all WindCube v2.1s. And if you want a full explanation, we've got an upcoming journal article that describes it in complete detail. Thanks for your attention, everyone.